So today we are going to introduce the second part of neural architecture search, which is a pretty exciting class. So before that, today, if you open mit.edu, our homepage highlighted our research on TinyML and on-device training. And so this is our upcoming new research paper on device training under 256 kilobytes of memory. That we are able to not only perform inference, but also train the model, fine-tune the model, customize the model on these edge devices. Okay, so that preserves the privacy, enables the model to be customizable, and also reduce the cost. Okay, so we are going to learn these on-device training techniques in later part of this semester. Okay, so here's a recap. Where are we so far, right? So we talked about neural architecture search, which has several components, starting with a search space. What are the design choices we're going to think about, right? The channel number, the depth, the width, the resolution, the kernel size, etc., defines the design space. And then the search strategy, whether we are using random search, evolution strategy, reinforcement learning, Bayesian optimization, these kind of search strategies. And also we need to understand what is the performance, how well does the model perform, right? So we need to have a feedback, which is the performance estimation strategy, including not only the accuracy, but also the latency and energy, etc. Right? So given an architecture, we want to have a performance estimation for the architecture. Okay. All right. So in this lecture, we are going to learn 3 parts. Okay. So discuss what are the possible choices for the performance estimation. Okay. How to efficiently search efficient models. And then we introduce this hardware-aware neural architecture search techniques. Okay, to enable the model to be not only accurate, but also efficient on target hardware devices, from a single device to multiple devices. Okay. And finally, we are going to introduce several applications that we can accelerate by using such neural architecture search techniques. And we're going to show several demos and comparisons before neural architecture search and after neural architecture search. Okay, so let's start by jumping into the first part, performance estimation. Imagine a very simple approach to estimate the performance of architecture is just to train it, right? You train the model on a particular data set, maybe a smaller data set, you train it for a while and see how well does it perform, right? So this requires a lot of iterations, right? You have to train the model, require a pretty large amount of GPU hours, right? So for example, if you want to search the model on ImageNet, training ImageNet takes several hours or days, right? So people tend to use a smaller design space, right? To smaller data set to train the model, okay? And the drawback is that the training cost is high since we have to train and evaluate many different models, right? For example, the controller propose the architecture with probability P, then we have to train this model, okay? And then return the accuracy, right? So after several such iterations, it can be quite expensive. For example, even training on Cypher 10, this work in neural architecture search, have to train 12,000, okay, 12,000 model architectures, which is taking 22,000 GPU hours, right? So that's quite a lot amount of computational effort and cost in order to do neural architecture search. Not to mention these large-scale data sets. Say we want to find a good model on ImageNet, we want to find a good model on the Coco data set. How do we do about that, right? Rather than directly training the model from scratch, can we stand on the shoulder of giants, right? So rather than reinitialize everything, can we inherit the weights? Okay, so this is another possible idea. For example, given a model that is previously a narrow model, without any training, I can make it wider, right? By splitting this weight. Okay, for example, splitting this weight C and split the weight D by copying them twice. Okay, so previously we have this H2 hidden activation. Now we have 2 copies of that, right? So this is net to wider net. So this node can be duplicated, and the weight here is made to be half of its original value half. Now it's half f. Okay, and we are duplicating this C and D to have 2 copies of C and also 2 copies of D in this case, right? So this is net to a wider net. So without any retraining, either directly copy the weight or make the weight by half. Okay. Another approach is basically net to deeper net. Say you originally have a 1-layer net, but you want to increase its capacity, right? You want to train it on larger scale data sets, but you don't want to train the deeper net from scratch. Okay, so what do? So you can initialize a layer with identity mapping, right? Identity mapping is just like you didn't have to anything, right? So it's still identical with the original model, but now you can initialize the model with such 2 layers rather than originally is 1 layer. Okay, and you can train the model starting from this model as a starting point, okay, rather than starting this model as a starting point, which gives you more capacity. Okay, so this is the foundation. And what we can do about it for neural architecture search. So remember in the recurrent neural net, previously we are directly giving the model architecture. Right now we are giving the decisions whether it's net to wider net or it's net to deeper net. We are giving those choices. Okay, so given a choice, we no longer have to retrain the model from scratch, but we can stand on the original network's initialization and train on top of it, either make it wider or make it deeper, okay, or no change. Okay, so in this way, we don't have to retrain the model each time. Question?
Sorry, we have always been trying to make things smaller, but why are we making it a network wider? Like,
so you make the network wider because you want to have more capacity, have higher accuracy.
so if it's exactly the same weight, doesn't make sense to me. The input is still the same size, and you're actually making it wider in a way that will end up in the same result.
No, they make a lot of sense because this is just initialization. Okay, you are not directly deploying this model, but you are training on top of this model. So after a training for a while, this is no longer f/2. This is no longer f/2, but there will be new ways they can adjust themselves. This is just the initialization, and you train on top of this model, get a larger capacity.
Do we keep the input the same size?
You don't change the input, you change the intermediate activation capacity, the input intermediate number of channels. Okay, so this is the method for weight inheritance. Okay? In short, you are standing on the shoulders of giants, right? Rather than reinitialize from scratch each time. All right, and then there's another interesting idea, which is using this hyper network, okay, which is a weight generator. So the weight of this network is not trained, but they are generated by another neural network called a hyper network. Okay, you train a hyper network to generate the weights for the sampled network architecture. So at each training step, a random model architecture is sampled from the search space. And how do we fill in the weights? Okay, so there is a weight generator network called a hyper network that generates the weights based on the model architecture. Okay, and we can use gradient descent to update the weights of the hyper network, which is used to generate the weight for the searched network. Okay, and then we sample the random seed and evaluate the error for this the weights of the network. Okay, it's original W, but it's actually W equal to HC, which is generated by this hyper network. Okay, so this is like the original network architecture. This is the encoding, and then we encode to the feature extraction for the encoded architecture, and then we have a shared NLP from the architecture to generate the weights for that architecture, and then we fill in the weights of the network architecture using the generated weights. Okay, it's like adding a level of indirection.
So the weight generation is just also to initialize that network. So we will then train the network, or it's
You directly use the magic part is that you just use that weight to run inference for that model.
okay.
Yeah.
So we don't do any training on the network anymore. Then. Only on the hyper network.
You train only the hyper network, which is used to generate the weights for the desired network. That's how it works. But this method is not actually quite widely used, just a very fancy idea. So, all right, another widely used idea is actually weight sharing. Right? So rather than keeping every weight independent, you have to train them from scratch all the time. What about we share the weights between different sub networks? Okay, so we can train a super network that can paint the entire graph, all the possible connections, like node 1 can be connected to 3, 5, 2, 4, 6. So we connect all the dots here, and then we generate the architecture by extracting the subgraphs from the super network. And then during training time, we train the super network, and then we search based on a subnetwork. And finally, we train the selected subnetwork from scratch. But they still require training the subnetwork from scratch in the end. And later we are going to learn techniques called word-for-word network, but can also eliminate the final stage. Okay, each subnetwork can operate independently. Okay, so so far we talked about several techniques that require training. Okay, so in order to get the performance and accuracy, we need to train the model, which takes a long time and require a lot of GPU resources. There are other techniques that we can just, so without any training, just look at the architecture, feed it with some random inputs to estimate the performance without any training. Okay? If that works well, it will be super cheap, super fast to directly estimate whether it's a good model or it's a bad model without any training, only GPU hours, just by looking at the model. That sounds magic, right? So there are several research in this direction. So the first one is called ZNAS. Okay? So the idea is that given a neural network, okay, and then we initialize a random input, okay, and also we add a small perturbation to the original input x to be x prime, okay, and then we initialize all the neural network weights to follow a normal distribution. So you have architecture, you want to see if this architecture is good, but you don't train it. You just randomly initialize the weights. Okay, and then given this perturbation of input, we want to see how large is the output. Okay, if a good model should be sensitive to the input perturbations, that's the key intuition behind that. Okay, if you change the input, the output is supposed to be fluctuating as well, rather than you change the input, but the output completely stays the same, very insensitive. That's a heuristic to determine whether a model is a good model. Okay? There is another term in this evaluation, Z1 plus Z2, we talk about Z1, which is you change the input, you observe the output change, hope it to be large. But what is the second part? Okay, the second part is actually looking at the batch normalization for each layer, right? And we look at the standard deviation, calculate the mean of that standard deviation, and hoping that the different across different channels with different inputs, we hope different channels can learn different stuff. And among different inputs, we hope the standard deviation to be larger, right? So that's the second term we put in the final heuristic, right? So in summary, we have two terms, given change the input, observe the change of the output, and also observe the mean of the standard deviation about different channels, the BN layer of different channels. Okay? And in practice, this heuristic is working well for classification. Question?
Yeah, I was going to ask, like, couldn't the same logic of you want the output to change drastically when you change the input, you want it to be sensitive to the input, couldn't you make the same argument that might mean that your network's just not robust if you tweak the input very slightly and the output it was just completely different. Could you make the argument that it could be a sign of both being not robust or also being a good model by this definition?
So the question is, if the model is not robust, you change the input by just a little bit, then the output can change very dramatically, right? Let me see. So there are also two terms, right? So this is just part of the story. You also have the second term, right? Which is a standard deviation of the batch normalization layer. So this is just a heuristic, right? There might be the model like what you mentioned. But that's why this is we put it right here, because it cannot completely replace those models that require training. You have to give up something, right? Since you didn't train anything at all, you just look at the weights. So people propose such simple heuristics. Another heuristic, right? Without any training, just to look at the model and see if it is good model. Architecture is by this technique called grad sign. Okay, grad sign is basically look at the region for this area where given different inputs. Okay, so in this region, the gradient for the same input, the gradient for this model is negative. For this one is positive, right? So if you're doing optimization, if you're in this location, this one is putting it to the left, this one is putting it to the right, making the optimization very difficult. So this red region, and we try to minimize that red region. Okay, so this one is considered a better optimization landscape. Okay, so the region where the sign of the gradients corresponding to the same inputs, okay, they are different. The region is very narrow on these green parts. No matter if it's the loss function with respect to fx1 versus fx2, okay, they are both in the same direction with respect to the gradient. Okay, similar for this green region, they are both in the same direction. Okay, so in the situation is that a good model has this denser sample-wise local minima. Okay, the distance between the local minima points, theta 1 and theta 2, okay, should be smaller. So within that range, okay, the sign is different. One gradient is pulling it to one direction, the other gradient is pulling it to the other direction, which is a heuristic saying that it's difficult to optimize. But a good model should have a wider region where the gradient is having the same positive or negative sign. Okay. So put it together here, we just want to go through several different input samples, okay, and also go through the corresponding layers. And we want to try to calculate the sign of the gradient for different sample and for different layer. Okay. Finally, we are going to sum them up, okay, across these different layers for different samples. Okay, so this number should be smaller or equal to n, where this equal sign is achieved only when the gradients of all the samples are of the same size. Okay, so this is summing up a lot of positive one or negative one. Okay, even only if across all the samples, all the signs are the same, then we can achieve this equal sign. Okay, so we use this simple term, just calculate the gradient, okay, without any training, just feed it with some initialized, randomly selected initialization points and calculate the gradient. Actually, you don't need the full gradient, but you just need to have the sign of that gradient. Okay. All right, so those are several techniques that can give you the prediction, a rough prediction of the accuracy without having to train it. Okay. So in the next chapter, let's talk about hardware-aware NATs, right? So in this lecture, we are talking about efficient ML, right? So what does it mean, efficient? The training has to be efficient. The inference also has to be efficient. And for neural architecture search, the search process also has to be efficient, right? So we want to efficiently search efficient models, okay? Use much lower cost You don't want to spend 48,000 GPU hours to search a model, right? And also make sure the search model can run fast. Okay, so that's our goal. 2 points. The search has to be efficient. The search model has to be efficient. So if you look at the landscape, previously we are having a general model for different hardware platforms, right? So for example, we have Resident 50, we have Mobile V2. Those are very popular models these days. Okay, but you know the Raspberry Pi and the GPU has completely different memory resource, completely different power budget, right? It doesn't make sense just to scale maybe the channel to make them fit, right? But instead, we probably need specialized models, right, for different hardware platforms. Like for Raspberry Pi, which has limited memory and also limited computation, right, limited CPU width, we probably want a smaller, more depth-wise layers, right? And then for the GPU, we probably want to avoid those depth-wise layers, which has low parallelism. Okay, so we need to specialize and customize models for different hardware platforms. So that's our argument. But searching a specialized model for different hardware architecture, that is very expensive, right? So previous neural architecture search techniques require, like NASDAQ require 48,000 GPU hours, okay? Even on the Sci-Fi data set. That's equal to 5 years on a single GPU. So Google can afford it, but not everyone can afford it, right? Another work called DARTS, it takes 100 gigabytes of GPU of memory if we directly search on ImageNet. So the largest GPU memory we have as of today is 80 gigabytes, which is the Tesla A100 80 gigabyte version. Okay, so this is just too big for the GPU hours and also the GPU memory. So therefore, previous work need to utilize this kind of proxy tasks, okay, to save the search memory and the search cost. So what are those proxy tasks? So rather than directly find the model on the target task and target hardware, which is pretty expensive, we want to do something simple. Use it as a proxy task. For example, we can search a model that perform well on the Sci-Fi 10 data set. Okay, and then assume this model will also work well on ImageNet as a proxy task. Search on small data set rather than a large data set. Have a smaller search space. Okay, for example, we just repeat the same search the building block for different layers. Okay, layer 1, layer 2, we have repeated the same building block. Or we can have fewer epochs of training. So rather than train everything before when it converges, we just train a couple of epochs. Okay, if it is good, then we assume it is also good when it's trained till convergence. And finally, people use this flops and number of parameters rather than the latency as a proxy task for the target hardware. Assuming if we have less number of flops, if we have fewer number of parameters, the model is also going to be running fast. But is there some potential problems as using such proxy? What are the potential issues using such proxy tasks? So a model perform well on Sci-Fi may not perform well on ImageNet, right? Different capacity, different complexity, right? And if you just train a couple of epochs, maybe some model will converge fast in the first beginning epochs, but may not be as good when everyone is trained till convergence, right? And flops and parameter counts, we are also going to see examples where some models may have much fewer flops, but actually it can be slower. So a good approach we proposed a couple of years ago is called proxyless NAS, right? We can efficiently search on the target task and target hardware. And we make the search so efficient, we don't rely on training everything and repeat the training. If the model is bad, we throw it away. But we can just introduce both these weight parameters and also these architectural parameters. Okay. So say for this layer, we have 4 choices. We can have the 3x3 convolution, 5x5 convolution, identity, and coding layer. And how do we select which layer should we choose? And what is the trade-off here? Imagine the 3x3 convolution may have a faster latency, but 5x5 may be slower, but provide more capacity. Right? So we want to learn both this weight parameter and also the architectural parameter, which is the probability of choosing one of such operations. Like we have probability alpha choosing this 3x3, beta choosing this 5x5. Okay, we want to learn not only the weights, but also the probability of choosing different paths. Okay? And during runtime, we just select the architectural parameter, which is with the highest probability at inference time. Okay? So during only one pass of training, we can learn both these weight parameters as well as these architectural parameters. So we don't have to train the model. If it is bad, throw it away, find another model, retrain it, right? So that one requires many iterations of training, but this one only requires one pass of training, learning both the weight parameters and also these architectural parameters. Okay, so we build this over parameterized networks with all the candidate paths, like different kernel size, identity layer, coding layer, etc. All different candidate paths. So we simplify this NAS to be a single training process, right? Rather than many training process, evaluate the accuracy and start from scratch, right? So we are never starting from scratch, but we just train with a single process of this over parameterized network. Okay? And we can prune those redundant paths based on those architectural parameters. So finally, we just remove those architectural parameters with small probability and leave only one in the end when we are doing inference. Okay. So at training time, we want to binarize these architectural parameters from non-binary to the binary format. Okay. And we only allow one path of architecture to be active. In this case, for example, alpha is the largest. We only have the first path to be active. And in the second case, the second 5x5 convolution has the highest probability. Then we only activate this path. Okay. Therefore, the training memory footprint, we no longer have to put all the activations of different branches in the memory, but we only keep a small amount of them in the memory. Okay? So the memory footprint reduces from O(n) to O(1) in this case. So now, since our search would be really fast and efficient, we no longer have to rely on these proxy tasks to save the search time, right? So rather, we can directly search on the large scale data sets like ImageNet. Okay? And we can enable a much larger search space rather than repeat the building blocks. Okay? And also we can allow full training rather than just train for a couple of icons. And we can also use the profiled latency, the measured latency, rather than using the number of parameters and also the flop counts. Let me make a pause. So, are there any questions for proxy NAS?
Yeah, I didn't understand how you update all the parameters at the same time with only one path for each trace.
So here we everything is differentiable, right? So here each time actually we choose 2 paths, okay, during the training time. So that's some of detail. You can also choose 3 if you have enough GPU memory. And so that's how we decide to update the relative weights of different parameters. And the naive approach is to have everything in the GPU memory, but that requires a lot of memory. It can easily explode.
But if we have two tabs, do we combine their output somehow, or we keep their output separate?
You can combine their outputs.
Okay. But if we then well, if we suddenly then remove one of the tabs, the output is different, right?
It's different, but somehow it learns the fact that we can choose for this layer, we can choose these two, we can choose these two. So during the learning process, since it's trained in this way, it can learn a model that has such capability to perform such sampling. All right, so this is an example where we are showing where the max or flops is not a good representation for the latency. Right? For example, there are three models. This one is MobileNet V2, okay, and this one is NASNet, and this is MobileNet. Right? So these two models, NASNet and MobileNet, both have smaller number of max compared with MobileNet V2. Okay? However, they have much higher latency measured on the phone. One is about 100. This is about 140 milliseconds. Okay, but these two are way over 180 milliseconds. Right. So max doesn't mean the real measured hardware latency. Okay. Similar for this case, the x-axis is the number of flops. The y-axis is the GPU measure the GPU latency. So we can either scale the dimensions, okay, the channel number. We can also scale the depths, okay, the number of layers, which is the depths. And we can find, although these two models have very similar flops, but increasing the number of layers can drastically increase the latency, but increasing the hidden dimension doesn't quite increase the latency. Right? So same flops, they can have drastically different latency. This is another experiment we measured on the Raspberry Pi. Right? So Raspberry Pi is greatly influenced by the hidden dimension. If we increase the hidden dimension, the latency on Raspberry Pi will increase very fast. But if we increase the number of computation, the GPU latency is not quite influenced because the GPU has a large parallelism. So you provide more parallelism, it's just preventing it from being starving. Right? So latency is not going to change much. So all these stories are just telling latency is not a flops or max is not a good approximation for latency. So therefore, it's crucial that we incorporate the latency feedback into the neural architecture search process. So of course, we can, given the proposed neural architecture, we measure the latency and we return this measured latency. But usually, since we have to very frequently measure the latency during training, it can be very expensive to build a mobile farm. Okay? And also it suffers from this heating, all these kind of issues. Right? So we can build a latency predictor, right? So rather than directly measure the latency, we can actually train this latency model from this latency data set. Given the architecture, predict the inference latency. Okay. So there are several approaches to perform this latency prediction. So we can compose a data set consists of the architecture and also the latency. For certain frameworks, we can also obtain this layer-wise latency. Okay, so for different layer, they can give the latency for running different layers. Like the first convolution layer, what is the millisecond? For second convolution layer, what is the millisecond? Okay, so in that way, we can construct this latency lookup table. So the next time we look at this second operator, we can just reuse the same latency since it has previously been measured. Okay, so this is for creating this latency lookup table. Say a convolution with resolution 122 by 112 by 112, already 64 input channels, 256 output channels. The same layer might appear in both neural network 1 and also neural network 2. This is like if you measure that latency for that layer in the first neural network, you just reuse this latency for the second neural network, assuming that there's no layer fusion and all the layers are independent. This is mostly the case for this normal convolution layer, but may not be the case for the steps-wise convolution layer, since several frameworks might be able to do such automatic layer fusion. So for example, this is a latency example latency lookup table. So the signature is, so this is the resolution 112 by 112 by 24. Output also have 24 channels and expanding for the inverted bottleneck, it's 24 channels, 3 by 3. Kernel size stride equal to 1. There's no IC, right? So this is the key. So we have this value, which is the predicted latency. We also have the mean and also the standard deviation. So this is an example latency lookup table. So such prediction-based method can be quite accurate compared with measure the latency on the real device. And so this is the estimated latency that we can achieve on the phone, right? And this is the real latency and measured latency. We can see they follow this y equal to x trend pretty well by using such latency lookup table. Okay. Sometimes we don't have the luxury for this layer-wise latency providing. Sometimes we can only get the whole network's latency rather than layer-wise latency. For certain frameworks, it will be slower if you enable such layer-wise latency providing, right? So we can only get the whole model's latency rather than the latency for each layer. So in that case, what do we do? So we can train this latency prediction model. The input is the dimensions, right? Including the kernel size of the layer, the width, the resolution, okay, for each layer. And finally, we can construct this fully connected, several fully connected layers to predict the final latency. Okay, so in that way, we can also have a very accurate latency predictor. The predicted latency is pretty close to the real latency. So as a result, we can have a pretty good speed up by using proximate NAS combined with the latency prediction, right? To have a faster model. So this is the latency, so this is accuracy. So about 80% faster than the baseline model, but have very similar accuracy. And the interesting thing is that we construct this table, right? We can use proximate NAS to search the best model for GPU, for CPU, and for mobile, right? So we can measure these three models on the GPU, on the CPU, and on the mobile, right? And we can see this diagonal pattern where the model that is designed for GPU works best for the GPU, right? Although they have very similar accuracy, but the model designed for the CPU doesn't run quite as fast as the GPU, right? So this is showing the necessity for such specialization. CPU and GPU and mobile, they prefer completely different model architectures. So such specialization enables better efficiency. Similarly for the mobile, so the NAS designed for mobile, it runs fastest on the mobile compared with running that on the CPU and running on the GPU. And here we want to visualize what is this process of proximate NAS, right? We have a single search and training process. We combine the training and search in the same pass, right? And what happens during this pass? So this is the history of finding an efficient mobile model. This is the history of finding the CPU model versus the search history of finding efficient GPU model. So in conventional training, we just fix the architecture. We just train the weights. right? But here we are actually not only, let's review it again. We are not only training the weights, but also the architecture can change during each training iteration. Okay? And here we find that the GPU model started to be pretty deep. Okay? And after a couple of epochs of training, it starts to use these wider layers, okay? A larger kernel size, but the depth is getting shallower and shallower. Okay, due to the GPU has pretty, you see, it's get shallower again. The GPU has large parallelism. It prefers less number of kernel cores. That's why it prefers such shallow but wide models, right? So these red layers are 7x7 convolution. These orange are 5x5, and the blue is 3x3 convolution. Okay? And we can see such efficient mobile model and CPU model, they are deeper, especially the CPU model also prefers to use many small 3x3 convolutions, as opposed to the GPU is using a lot of 7x7 convolutions to saturate its parallelism. Okay? So it's very interesting that for different hardware platforms, we can actually search specialized models. And also the training process is no longer fixing the architecture, you just train it, but also we can actually change the architecture during training. All right, so so far we talk about given a single model, right? How do we find a good model for that? What about we have multiple devices, right? So the search cost to find a specialized model for each platform is going to increase very fast, right? So in the second part of this lecture, we'll talk about the once-for-all network that can target designing just one model, but later you can specialize it for different hardware platforms, large and small. Okay? Just pay the training overhead only once. So we talk about we want to not only search the model for just one hardware platform, but there's just so many, there's diverse hardware platforms like the GPU models on the cloud, TPU on the cloud. You have Qualcomm DSPs in your phones, you have all kinds of different accelerators or even ARM processors with these microcontrollers. And so a lot of big models are actually heavily optimized for GPUs, but they may not fit quite well on other platforms. Right? So how do we efficiently customize the model for and adapt the model for different hardware platforms? Original way, right? We train a network, get the accuracy and the latency, see if it is a good model. If it is not, then we have to repeat this process. So this training process, like we mentioned, is quite expensive. But how about we train this once-for-all network? Okay, so you just train it once, and then you can select a sub-network to get the accuracy and latency. You can try subnetwork A, subnetwork B, many different subnetworks. They are trained such that different subnetworks can operate independently, right? So we no longer require training for this accuracy and latency, this kind of selection, but we can just directly obtain the model by sampling from a once-for-all network, okay, which can amortize the cost. What about if we have a new hardware platform? We just redo this search rather than having to redo this training. Okay. So such automatic design process, right, can synthesize neural net to fit a particular latency, accuracy, and also memory constraints. Okay. It's like EDA tool for circuit. Okay, so this is the neural architecture search for neural nets. Okay, now we train it, evaluate if it's not good or not, either keep it or resample it. Okay, so that's the traditional way. But now we are training this once-for-all network. Okay. It contains many different child networks that are sparsely activated. So this is during training. Okay. At search time, okay, given a more a chip with more computational resource like Snapdragon 8 Gen 1, we can select a larger subnet. And with an older generation of chip like Snapdragon 855 SoC, we can select a smaller subnetwork. And all these subnetworks are actually directly sampled from this once-for-all model. Okay, they share the weight. For example, the weight is directly obtained from this super network. Okay, we train once, and then we can get many to fit diverse hardware platforms. And similarly for microcontrollers, we may have different memory budgets, like 12 kilobytes of SRAM, 2 megabytes of flash, versus a smaller Cortex and 4 microcontroller that has 256 kilobytes of SRAM and only 1 megabyte of flash. Okay, so rather than repeating this training and search process for different microcontrollers, we can just train the super network once, okay, and then find specialized subnets for different scenarios. And this will be part of the homework. We will give you this once for a network. And the magic part is that you don't have to retrain it, but you can directly obtain these subnets that you can evaluate its accuracy and latency. They can independently operate. Okay, of course, if you fine tune it for a while, it's going to further increase the accuracy. Similarly for newer generations of phones and also older generation of phones. So we want to be inclusive for users who have newer phones and also for users who have older phones, right? So rather than having to ship different versions of models to the App Store, we can just ship one model and then at runtime research different subnets for different constraints.
How is the memory used to constrain the search within the subnet? Like, is it the same search going on, but like if it violates the memory, it just returns infinity or something? Or
Yeah, so the question is, how do we fit a particular memory constraint? Right? So here we have our target, we have our target latency, accuracy, and maybe also the latency constraint, right? So if we find a search in subnetwork, but it doesn't satisfy our memory constraint, then we have to resample another subnetwork until it reaches our target latency, target memory, and also target accuracy. And since this one small model contains such large amount of subnetworks, you can actually have a lot of choices encoded into the super network. And similarly for the full battery scenario in the morning, you can run this larger subnet. Okay, and in the evening, when you have in the battery saving mode, rather than getting the app completely dead, right? You can run a smaller subnet without having to maintain multiple copies of the model. But just have one copy, but it can be different parts can be activated. And we find it surprisingly, we can train as many of 10 to the 19th different subnetworks at the same time, okay, for image classification tasks. Okay? So we have this train the super this one's for network and get many different child networks for different hardware platforms. Okay, so this one's for model short for OFA contains many child networks that are sparsely activated. And these child networks share the weights with the one's for network. And they are trained jointly. So this model, they all share the weights and train jointly. Amortize this training cost. Pay the cost only once, but we can have different deployment scenarios. And then we can design such specialized neural net models for different hardware platforms, right? For the GPU, for the mobile, for the microcontrollers. So how does it work? How do we enable the model to have different subnetworks that can independently operate? So here there is a technique called progressive shrinking. Okay, so we can progressively shrink the kernel size, the number of layers, and also the number of channels. Okay, so here we start with this 7x7 kernel, and then we have a transformation matrix to train this 5x5, and then we train this 3x3. They share the weights. For example, this 5x5 are directly transformed from the middle 5x5 weights from the 7x7 layer. And similarly, these 9 weights in the 3x3 kernel are actually shared with the original 9 weights in the center of this 5x5 kernel. With respect to the number of layers, initially we train with all these 4 layers. right? And then we shrink the depth, we can shrink with 3 layers, we can also shrink with 4 layers. And then we further shrink the depth, we can shrink 2 layers, 3 layers, and 4 layers. Okay, so this is progressively allow a smaller number of depth. And for the width, number of channels, we start by treating all the channels. And then we learn this channel importance. We sort it, reorganize that such that we can train even smaller amount, only 3 channels rather than 4 channels. And then either 2 channels, 3 channels, or 4 channels. Okay, so this is basically the steps of progressive shrinking. So shrinking the resolution, large resolution and small resolution, and the elastic kernel size from large kernel to small kernel, and elastic depth, all the depths, or a shallower version of that, and train this elastic width, either all the channels or half of the channels, right? So this is progressively prune the kernel size, the depth, the width, and also the resolution, such that we can obtain this transform network that have different subcomponents that can independently operate. So let's examine the hardware behavior of such a transform model. So let me introduce this roofline analysis, which is very commonly used technique when we are characterizing the performance on the hardware, right? So here, the x-axis is operations per byte, indicating when you fetch 1 byte of memory, 1 byte of data from memory, how many operations can you perform on top of this byte of data before you throw it away, right? So the more, it means you can do as much of, you can do more computations given the same amount of memory footprint. Okay? Since we mentioned in this class, memory is very expensive, but computation is cheap, right? So you want to fetch 1 byte of data, but do as much of computation on top of this data, right? So ideally, we can improve the efficiency usually by increasing the operations per byte of our application. And the y-axis is the giga operations per second we can achieve, saying what is the throughput of the machine running such algorithm, right? So here we compare the widely used MobileNet and also this MNASnet versus this one-for-all network, right? So for this one-for-all network, it's in this point compared with these points. So this is in log scale. Actually, here and here they differ a lot, right? So here we can find this one-for-all network. It's more operations per byte, right? We can perform more operation given the same memory footprint. Therefore, it has a larger throughput, larger GOPS per second. So this is another way to understand this figure. So everything is measured on the 0.3 FPGA. Right? So at MNASnet in MobileNet the measured throughput is about 40 gigaops per second. But for this one-for-all network, it can achieve 76 gigaops per second, just because it is less memory bounded, right? For inference, we want to make sure the model is not memory bounded, since memory is very expensive. Right? So why OFE model, search model is good? Because really the search model have a higher arithmetic intensity. Okay, and how is that achieved? Because we feed the latency during the design process, so it can automatically find the model that has high accuracy and also lower latency. We didn't teach this NAS process, what is good, what is the operations per byte, but it can figure out such details by just giving it a end-to-end supervision by providing it the latency. So this is performance of this one-for-all model on diverse hardware platforms, including the Samsung phone, Google phone, LG phone, the GPU, the CPU, and FPGAs. Right? For example, on the GPU, we can reduce the latency from this is about 28 milliseconds to only like 12 milliseconds, right? With the same or even better accuracy. So conventional pruning or quantization techniques, they can preserve the accuracy, right? But here we can actually improve the accuracy by finding a completely new model. And similarly, for the FPGA, you can reduce the latency from roughly 6 milliseconds to about 4 milliseconds. Right? All right, so far we talked about a lot of neural architecture search techniques. What about we combine the hardware architecture search, right? Since we have different configurations for the neural network architecture, we also have a lot of choices for the neural network accelerator. Can we co-design them together, right? So we want to have this data-driven approach. We don't want to rely on many human expert knowledge. By using this data-driven approach to run a lot of configurations, lots of feedback, and let the system automatically figure out what is the best accelerator, and what is the best neural network architecture that fit such neural network accelerator. Okay. But the existing like hardware-aware NAS technique and also this compiler technique, we just only assume those off-the-shelf hardware, right? Not customized hardware accelerator. And also I neglect the freedom in the hardware design space. So what if we have the choice to take out our own chips or design our own accelerators, right? So let's see what are the new choices we can have. So we can have different choices for the buffer size, right? Global buffer size, number of PEs. What are the connectivity about the PEs? Compute arrays, right? And also loop orders, loop tiling size, the data flow beyond this layer channel, kernel size, bypass layer, weight, precision, etc. Right? So we want to incorporate this accelerator architecture search in the same loop with this neural architecture search. Okay, to propose the best matched accelerator and also neural network models. So let's talk briefly. How do we co-search the accelerator architectures? Like we mentioned, we introduced a larger design space compared with just the neural network architecture. Now we also have this architecture sizing and also these connectivity parameters on the hardware side. It's like opening a much larger design space. But how do we search on that design space, right? So there are several categories, right? We can have this decision about the hardware parallelism. So which dimensions in the for loop of a convolution we want to parallelize them in space rather than serialize them in time. And what is the loop order? What is the tiling strategy? Okay, and how do we map it to the hardware, right? So there are roughly two categories. One is the numerical values, like the buffer size, the dimensions, the panel size, so-called, right? Those are easy since they are just a numerical number. The difficult part is really the non-numerical parts, right? Like the parallel dimension, the loop order, right? So a simple approach, maybe just use this index-based encoding, right? So for this loop order of CR, X, KYS, we just encode it to 0. Another one we encode it with 1. But the difficulty here is the increment or decrement of index values doesn't mean anything, right? You cannot say this is larger than this one since you cannot directly compare these different loop orders. So other approach. So another approach is actually learn the importance of different parallel dimensions, right? For example, we can fix the position in the encoding vector. This is for the parallel dimension and also for the loop order. We just want to learn the order, right? And then we can assign it a numerical importance and then do evolution or do some search on top of that, right? And we can sample according to our multivariate normal distribution, for example. And then we can sort it. And the largest one is corresponding to the most important dimension, which we are going to put it in the outer loop since it has the best locality. So we choose the first two dimensions to parallelize as the outer loop, or put it to parallelize in space. And also we can choose the loop order. This is the outermost, since the important dimensions, we wanted to have the best locality, so prevent swapping, versus the least important we put in the inner loop. It will be swapped a lot. So finally, we can make the decision like this. So look at the color. For example, here we choose the first two dimensions, which is C and K. Okay, we do parallel or indicating that they are parallelized in space. For the remaining, they are serialized in time. Okay, so those are for the red color. And then for this light green color, okay, we choose such loop order such that this is from outermost to innermost, from CRXK, this is CRXK, right? So this is how do we learn those non-numerical values, right? And for these numerical values, they are actually relatively simple. For example, the size of the of different buffers of the different tiling size, we can derive it from these numerical values. For these different tiling sizes, we can also obtain them from these blue colors, right? So this is how we combine both these numerical values and these non-numerical values, including the parallel dimension, loop order, as well as those tiling size and other connectivity parameters into one search space. We can use evolution strategy to search. So this is the joint optimization of 3 steps: the neural network architecture, the mapping strategy, and here the accelerator architecture, right? So here we use evolution for all these scenarios, okay? And this is the follow that we first generate a accelerator architecture, and then we are given a group of neural network architecture proposal, right? And for each neural net, since we are having a pool of a neural network benchmark, we want to find for each neural network, we want to optimize the mapping given a accelerator architecture. Okay, and we update using our optimizer to update both the mapping and also the hardware accelerator, right? So this is really tightly coupling the design for the neural network accelerator architecture and the neural network architecture. So basically, this is comparing the architecture sizing only versus combining the numerical values and also the non-numerical connectivity all together in consideration. So this is EDP reduction, showing that the neural accelerator architecture co-search can find a better configuration than just finding this architecture sizing only, right? And this is the benchmark basically in the cloud and also on the edge devices for different benchmarks. What is the speed up over the baseline on different neural networks? We can see both the speed up and energy efficiency is actually quite good by opening up a large design space and have a systematic approach to learn not only those numerical hyperparameters, but also those connectivities. So this is the energy delay product versus the accuracy trade-off curve, right? So we started with the baseline human design, the human design for the neural net and also the accelerator. So with hardware architecture search, we can maintain the accuracy and find a better neural network accelerator architecture that gives about 4x energy delay product reduction. And by combining hardware architecture search and the neural architecture search, we can further increase the accuracy by 2.7%. Okay. And on the right-hand side, it's basically showing the AS designed data flow, okay, which chooses to parallelize the output height and also the output channel dimension, which is quite different from the human design. And also chose buffer size to be 496 byte, and also auto buffer size to be 107 kilobyte. So none of these are manually specified, but through this data-driven approach from this neural accelerator architecture search. All right, so let's switch gears to talk about the applications of NAS. So we have designed so much for NAS. What can NAS do for us? So this is NAS for point cloud understanding. So basically, the self-driving cars are equipped with LiDARs. Okay, so those LiDAR sensors have to process those highly sparse input data. Okay? Previously, they run quite slowly on the GPU, but the search model actually can run almost 3 times faster compared with baseline model. So here we are basically designing this one small approach to train a supernet that contain different depths, okay, and uses progressive shrinking to start with depths of 3, 2, and 3, and finally 1, 2, and 3. Okay, and also support fine-grained channel number selection, right? And we use this evolutionary strategy. Like in last lecture, we talked about to mutate and also to cross over to find the next generation of population. Okay, and we use the supernet-based approach to support to use weight sharing to support elastic channel number and also the depth. Similarly, this one small technique also works well for transformers and also natural language processing. So we can build this one small transformer and then have different specialized version, large and small, large for the GPU, small for the IoT devices. Okay, and we can reduce the latency and model size at 2 to 7 and 2 to 4 times. This is the showing the one small network for the scan models, right? So initially using the scan models to do photo editing is pretty slow. It's taking around 3 seconds to run the scan model on the laptop, right? Because we are doing such pixel-wise prediction. We have to accurately predict each pixel of output, which is a lot of computation, right? So we want to run this one small technique so that during editing time, we can run a small subnet, which is more responsive, right? So finally, during the finalization stage, we can run this larger subnet. Okay, so now let's try to use this any cost again. So here I make the ladies now. You can see it's becoming much faster, right? Only 0.39 seconds compared with 3 seconds. And we can add other features. Although we are using a smaller subnetwork, we can see the output quality actually doesn't degrade very much. Still pretty high fidelity output quality. So finally, we can click this finalize button to run the full model and get the final model.
Yeah, why is that faster? You don't know the small subnet and large subnet competitors. So
Oh, actually, it's just going through the smaller subnet to give you the final DC prediction.
so what's the finalization?
Finalization is after you change the different configurations, you want to click the button, run the full model to give you the best quality model, right? This model has slightly better accuracy than this one, but this one is a lot faster for interactive photo editing. We can watch this again. So after everything is done, we click the finalize button. And that's it, we are going to deliver that. No longer make more edits. Actually, there's a third one, I think, in the demo. We can watch again to distinguish between this editing mode versus finalize mode. So now we are in the editing mode, and we can try different configurations. Pull the bar, and maybe add an eyeglass. This is running the smaller subnet. And finally, we are done. We click the finalize button to run the full model to give the final high quality image. Does that make sense? Okay, good. Okay, finally, we have this one small network for pose estimation. We have seen this in on the phone, right? And actually, this NAS designed model can have up to about 4.9x latency reduction compared with the baseline model, okay? Running in real time on this Qualcomm Snapdragon 855 mobile SoC. This is actually quite an old SoC. Even the old SoC, we can run it in real time. There are more applications that can be enabled and accelerated without having to buy new chips, but even using the Raspberry Pi, we can do the phase estimation driver monitor to see whether people is fatigued, whether they are distracted, right, on these low cost hardware devices. And those hopefully can give you some idea for your final project. Okay. Recently, we even employed such technique to quantum AI, right? So for quantum AI, they suffer greatly from this noise, right? So the gates are very, very noisy. So there is a large gap between this noise-free simulation versus this measured items. Right? This is quantum neural nets deployed on this IBM Yorktown device. So a huge gap due to the noise. So if you have more gates, likely to have more noise. So how do we selectively choose which gates is necessary, which gate is not necessary? So we train this super circuit that contain different configurations of gates. And at runtime, we can at search time, we select different sub circuits and find the best trade-off between to find the sub network that gives the best accuracy. That it may not have the most number of gates, because fewer number of gates will have less noise, but fewer number of gates also have less capacity. So this new borrowing this new architecture search technique, we can actually improve the at least 4 accuracy from 47% all the way to about 85%. Still at early stage, right? Only 85%, but it's a big improvement. And we have open source this library. Feel free to try that. We are going to have like 3 lectures toward the end of this semester to talk about quantum and quantum neural nets. All right, so here's a summary for today's lecture. We learned about how to run performance estimation, build the latency lookup table, run latency models, right? Hardware aware NAS using proxyless NAS to directly search the model for target task and target hardware, right? And also once for all network that can easily find different sub-networks for diverse hardware platforms and train only one once for all network. We discussed the several applications of NAS. Okay. So in the next lecture, alumni Dr. Lucas will give a guest lecture to talk about his experience in industry, how we can apply this neural architecture search to build real world products. So if you're interested in internship or understand what we learned, how they can be applied to real world applications, next lecture will be very fun. Okay. All right, that's all for today's lecture. Thank you.